Hi there, this is Dr. Emanacker. I wanted in this video to do two things. One, briefly go over how the technique for solving Bernoulli equations comes about. And in going through that, I want to provide some of the algebraic detail, if you would, on how things happen. Um, Secondly, I want to take a look at solving a problem, which is actually a Bernoulli equation, applying this technique. Okay, so first, what is the equation going to be in the form of to identify it as a Bernoulli equation? Well, what we're going to have is our y prime, then we're going to have our y, and then a real solid indicator is over on the right-hand side. It could be on the left-hand side and just need to be moved over. We're going to have y to some power. For example, y cubed, y to the fifth, y squared, something or other. The other element of a Bernoulli equation is you're going to have your y value. It could be multiplied by something or other. This something or other could be something as simple as 1 or 2, or it could be something like x squared plus 3x. But whatever that is multiplied by, it's going to be some function of x. And on the right-hand side, your y to whatever the power is going to be is also multiplied by some different function of x. Could be the same, but most likely different. Okay, so to go about solving these, what you want to do first is to divide by y to the n. And when you divide by y to the n, you're going to get y to the negative 1, y prime, plus p of x, y divided by y to the n, plus q of x. So on the right-hand side, your y to whatever the power is going to go away. On the left-hand side, you're going to have this y to the negative 1 y prime. But what I'm primarily interested in at this step right here is this y, no derivative involved, raised to the 1 minus n power. Notice this 1 minus n comes from the equation directly above it where you have y to the 1 divided by y to the n. Using your properties of exponents, that's equal to y to the 1 minus n. Okay, so we're going to use this y to the 1 minus n and define that as our u. We're going to do a substitution. We're going to substitute our y for u. And we're going to set u equal to y to the 1 minus n, that 1 minus n being right there, and we just discussed where that came from. From that, you then go ahead and you take the derivative, because we're going to need u prime as well, and you take the derivative using the chain rule. When we take the derivative of y to the 1 minus n, the 1 minus n in the exponent becomes the coefficient, and then you take whatever your exponent was and you subtract 1. So you get 1 minus n minus 1. Once you have that done, you now take the derivative of whatever y is. So we're going to get y prime. This is a chain rule. Combining like terms in the exponent, we're going to wind up with 1 minus n minus 1. Well, the 1 minus 1 cancels, and you wind up with u prime equals 1 minus n times n to the negative 1 times y prime. Okay, in our particular situation, we have for our lead term, you can see it at the top of the screen, y to the negative n times y prime. However, if you'll notice, we really want to have this. We want to have 1 minus n y to the negative 1 y prime. Okay, so how are we going to adjust that? Well, it's not a horribly difficult thing to do because remember, n is going to be a number like 5 or 2. It's an exponent. And 1 minus that number is just going to be a number. I can take my y to the negative n y prime and rewrite that as something like this. I know I want a coefficient of 1 minus n included, so I offset that by multiplying as well by the reciprocal, 1 over 1 minus n. And remember this, 1 minus n is going to be a number like negative 2 or negative 4. So this fraction at the front is just going to be 1 over -2 or -3, whatever it is. So what we now have is a situation where we have our 1 minus n, y to the n minus 1 y prime, but it's all multiplied by 1 over 1 minus n. This entire part inside the yellow brackets is just u prime, which allows us to rewrite this whole first term as 1 over 1 minus n u prime. When you do this, you come up with an equation like this. You get 1 over 1 minus n u prime plus p of x times u equals q of x. Notice what you now have is a linear first order equation, which is a lot more straightforward to solve. As an example of how to apply this, let's take a look at the following. Let's say you have the equation y prime minus y over x equals minus y squared over x. This can be rewritten as 1 over x times y, and here it's going to be a minus 1 over x times y squared. So I've just separated out my coefficients that are some factor or function of x from the y. Okay, I can now see, yep, we have a y squared over here, so this is set up as a Bernoulli. I'm going to go ahead and divide everything by y squared. When I divide by y squared, it's going to give me this equation right here. And at this time, I'm also going to write down what I'm going to do for my substitution. I'm going to let my u equal to y raised to the 1 minus n, but in this case, n is 2. So I'm going to set u equal to y to the -1. Taking the derivative of u using the chain rule, the -1 comes out front. We're going to have y to the -2. Remember, you subtract 1 from the exponent. And then you're going to have times the derivative of the inside, the y. So you get a negative y to the -2 y prime. Okay, let's take a look at how our equation started out. It's at the top of the screen. We have this y to the -2 y prime. What we really want is negative y to the -2 y prime. Well, that's easy enough to fix. I'm going to put in that, I really want this negative y to the -2, put that 2 back in there, it disappeared, y prime. I'm going to put the negative in there that I want as part of my u prime, and to compensate for that, I'll just multiply out front by a negative. So this then allows me to rewrite my equation, substituting in u prime for the negative y to the -2 y prime, and substituting in u for y to the -1. All right, when I get to that line, we are now back to a linear first order equation. We have negative y prime or u prime minus 1 over x u equals -1 over x. Multiply all the way through by a -1, and it gives us the equation that I'm moving to the top of the screen right there. Linear first order, can solve this using an integration factor. What we need to do is first determine what is that factor going to be? What's its value of r or rho, depending on what book or person you're listening to. And we're going to wind up with rho, or r of x, is equal to e raised to the integral of 1 over x. And remember, this 1 over x comes from the function multiplied times u. And when you integrate that, you're going to get e raised to the natural log of x, but the e and the natural log cancel, giving you x. Okay, so what do I do with this x, my integration factor? I take this equation at the top, multiply everything by that integration factor, and that's going to give me xu prime plus u equals 1. On the left-hand side, this is really the result of the product rule applied to u times x or x times u, whichever way you want to list that. So I'm going to rewrite that as the derivative of the product of those two terms equals 1. Integrate both sides. So on the left-hand side, I'm going to have the integral of that derivative x times u, and on the right-hand side, I'm going to have the integral of 1 dx. On the left side, the integral and the derivative cancel out, leaving us with u times x. And on the right-hand side, when you integrate 1 with respect to x, you get x plus c. To solve for u, I'm going to divide by x. Now, when I divide by x, okay, I'm going to have u remaining on the left side. And on the right side, I'm going to have x divided by x, which is 1, plus c divided by x, which is c over x. Recall that earlier in the problem, we set our y to the negative 1 as u. We can substitute back, replacing u with y to the negative 1. And I'm going to take my two terms on the right-hand side, get a common denominator, and this gives me x plus c over x. So I have really 1 over y equals x plus c over x. To solve for y, you just take the reciprocal of each side, and there you have it. There's the solution.